I'm Michael Rosenthal, also from UC Santa Barbara.
Rachel Smullen, University of Arizona.
I'm Cassandra Anderson at Cornell. I'm Dario Ruiz from the Australian National University.
I'm Rajika Kurawita, also from the Australian National University.
Skylar Wolf from Johns Hopkins University.
Lauren Biddle from Law Observatory.
Jorge Lillo Vox from Spain Astrobiology Center.
Maxwell Tsai from National Astronomical Observatory of China.
Ben Ren, Johns Hopkins.
John Zink from Cal State Northridge.
And I'm BJ Fulton from the Institute for Astronomy in Hawaii.
Okay. So we're Studley. It's pronounced that way. So the study of uniqueness of disk lifetimes for exosystems. So our group had to kind of see the effect of disk lifetimes on the exoplanet populations and what we would get. So next. So the first question that we had to answer was, how does the disk lifetime affect planet formation? So the obvious thing to do is to run population synthesis for varying disk lifetimes, which is what we did. And this is the result that we get. So I didn't get to put a legend on here, so I'll explain it. The red line is the population of giants. The blue and black dashed lines are the population of intermediate mass planets. The blue ones are the icy ones, the red ones are the rocky ones, and the top ones are the low mass icy and rocky planets. The criteria that define them is the same ones that Christoph uses in his simulation. So icy is determined by whether it's formed outside of the ice lines. That means it's icy. If it's formed within the ice line, then it's rocky. So as we vary the disk lifetime, we see that the population of giants increases with time, which kind of makes sense because you have a longer disk lifetime, you have more time to accrete a massive envelope. So that's what we observe over here. And as that happens, you get less rocky planets. Oh yeah, so by the way, the y-axis is the fraction of planets from the population synthesis. So each of them simulates 1,000 planets. So of that fraction, what are in each of the populations? So that's what we get from, that's how we see the population varies with lifetime. And if you want to try and compare it to observations, what we have observed for disk lifetimes is that it has a log normal distribution, so it peaks around 3 million years. And I guess you should see more smaller rocky planets compared to giant planets.
Okay. So we broke into smaller groups, and we were curious or wanted to investigate if there was a minimum lifetime required to form a Jupiter-like planet. So the first thing we did was to run a single planet simulation using the nominal parameters. Yeah. And then we varied the disk lifetime, as you can see at the top. So what's plotted here at the top, we're varying the disk lifetime. The green line is the core mass, the red line is the envelope mass, and the black is the total mass of the planet. So you can see that for low disk lifetimes, you start out with just accreting a core. There's not enough time to accrete an envelope before the disk all dissipates, and then rather rapidly, actually we've plotted it in the upper left there, at 1.2 million years, you rather rapidly start to accrete a very massive envelope, and then increasing the disk mass, or the disk lifetime past that, doesn't have much of a significant effect except to increase the total envelope and total mass. So from there, we then ran a population synthesis on 1,000 planets, again using the nominal values. And so we again are varying the disk lifetime. And then what we've done here is plotted semi-major axis and total mass and colored the planets according to how massive the envelope was. So if the envelope is 10 times the core mass or more, the dot is colored red. So you can see as we increase the disk lifetime, we see the mass of planets increasing, we start to get more and more Jupiter or gas giant planets, and we also see the effects of migration setting in as planets move more and more to the left. And then we pointed out two kind of key transitions here. The first in the upper left is where we see the first Jupiter-like planet appearing at 0.36 million years. So that's just one planet out of the 1,000 we generated. You can see in the upper left there. And then at 1.86 million years, we get the first hot Jupiter forming, which we defined by having a Jupiter mass planet, or Jupiter-like planet, interior to 0.1 AU.
Okay, our next question was to determine if there was a maximum lifetime to avoid all the planets migrating to the star. We initially thought that there might be some timeline where the stars would just start eating up the planets like Pac-Man pieces, you know, just start munching at them. But we were surprised and found out that with the nominal case, the migration is actually quite slow. And we can see here, if we run this, that we actually ran this for about 3 billion years. And our last case, we could still see we have a lot of planets there. And we even have a lot of Jupiters. The only thing we're really missing are these super Earths towards the end. And you can even see where they pile up. Here we have the type 1 migration, the type 2 up there. But a majority of the planets still stick around, which is kind of surprising. So obviously, migration has a very small effect on long time scales. And then we can see here that we actually graphed the percentage of the planets devoured by the star as a function of the disk lifetime. And we found that there was a best number was here at about 100 million years, or sorry, 10 million years. And about 6.2% of the planets were completely devoured. And at our maximum at 3 billion years, we still had about 3/4 of all the planets still there. So there's really no entire engulfing of all of the planets by our simulation. But I think if we had used the full migration, we would have seen this happen a lot faster. But like I said, we used a nominal, so I don't know, observation, theory, not matching for some reason there. And just to summarize, we had how does the disk lifetime affect the planet's formation? We found that the lifetime is proportional to the number of massive planets. And then, is there a minimum lifetime required to form Jupiter-like planets? Yes. I think we came, what was it, 0.5 to 2, 0.4 to 2-ish million years, right? And then, is there a maximum lifetime? Well, we clearly saw there's not a maximum lifetime based on the migration effects we had in this simulation. So, something to look forward to, I guess, or look into. All right, thank you. No, I mean, not that oh, okay. Is there any signature of devoured planets that we know of? Yeah, is there? Yeah, maybe I'm going to.
Because we believe that planets have an enhanced metallicity over their stars, there could be a slight enhancement in stellar atmospheric metallicity, but I'm not sure how we would distinguish that from a general stellar population.
In the build-up to migration, what was the cause of the build-up? You're talking about like the two lines that were right over here, right? So that's actually the inner radius of the disk, and one you could see there was the type 1. If we go back, blah, blah, blah. Oh no, I ruined it. Never mind. So we had two lines. There was type 1 and type 2, and the reason that the type 2 one was a little more inwards is because the type 2 migration can actually force those planets in a little more. There's a little more strength in the type 2 migration than there is in the type 1. Yeah, as you can see up there. Does that make sense? Hopefully.